In the previous video, I introduced you to projectile motion, and here we are going to look at projectile motion more closely and arrive at an equation for a body performing projectile motion. We will find out that the equation turns out to be the equation of a parabola. Right? So let's start. Let me first begin by drawing the y-axis and the x-axis. Right? So this is the y-axis that we are drawing, and this is the x-axis. Right? And let us say an object starts from here, from the origin of the axis, and it performs projectile motion. So it goes up like this and then comes down and hits the ground over here. Right? So this is the y-axis and this is the x-axis. So this is the origin and the starting point. Let us say somewhere over here we identify this as point P, the topmost point, right? When it is at the topmost height, let us call this as point Q, and let us say this is point R. Right? So the object is performing projectile motion and going along the path OPQR. When the object is over here, it will start off with some velocity u. We will call this initial velocity u, and the angle it will make will be theta. So let me show the velocity over here in the form of a vector. It will be a tangent at the origin, right? So this is the velocity u, right? And let us say it is making an angle theta 0 over here, right? Theta 0. So the angle made is theta 0, and this particular velocity, it is velocity. This velocity will have two components: one component along the x-axis and one along the y-axis. So let me show the components. So this particular component, right, this will be ux, meaning the component of u along the x-axis, and its magnitude will be u cos theta 0. This angle is theta 0. And this particular component, this one, right, this will be uy, which will be u sin theta 0. Similar thing will happen over here. If I show the velocity over here as tangent over here, this particular velocity will have two components. This is the vertical component, which we will call as Vx, and this is the horizontal component, which we will call as V. This is Vx rather, and this will be Vy. Right? So this velocity is V at point P over here. If I go to point Q, this is the object has reached its maximum height. Here the object will not have the y component because it's not moving along the y-axis. It will only have a horizontal component. So if I draw a tangent over here, right, this will be Vx, right, and there will be no Vy. Finally, when it reaches the ground over here, it will follow. The velocity will be over here, tangent over here. So I can show it like this, right, and then I can show the two components, right. Now this particular angle will be exactly theta 0, right? The same angle which we had over here. It will hit this ground at the same angle theta 0 with the x-axis. This angle over here is theta, right? And this would be the horizontal component Vx, and this would be the vertical component Vy. Right? So this is how the object is performing projectile motion. Now, we have discussed one property of projectile motion, and we said that the horizontal component of the velocity remains constant throughout. The horizontal component of the velocity is u cos theta 0, which is ux over here. This Vx, the horizontal component of the velocity, will be equal to u cos theta 0. This Vx will also be equal to u cos theta 0, and this Vx will also be u cos theta 0. The horizontal component remains constant. Reason? Because when the object is performing projectile motion, there is no force acting on it in the horizontal direction. The only force that is acting, as we've discussed earlier, is the gravitational force Fg. Right? So whatever change in velocity will only occur along the y-axis, no change along the x-axis, and therefore the x component of the velocity remains constant throughout. Okay. Now let us focus our attention on this particular point P. Right? When the object has reached over here, let us say it starts from over, reaches at point P in time t, right? And what is the distance it has covered along the x-axis and the y-axis? That is what we are going to focus our attention on. So the distance that it has covered along the y-axis will be this. Right? this much, which I'll denote by y. The distance that it has covered along the x-axis in time t is this, right, which I will denote by x, right? And the objective over here is to find out an equation for x and y, right? So let us begin. Let us begin with x, right? I want to find an equation for x. X is displacement. Now displacement in this case will be equal to the velocity in the horizontal direction, because we are talking of displacement along the horizontal direction. So the velocity along the horizontal direction is u cos theta 0, and also this component u cos theta 0 is constant throughout. So I can directly use the equation x is equal to this displacement is equal to u cos theta 0 into time t, right? Because u cos theta is 0. And therefore t is equal to x by u cos theta 0. Right? I'll call this equation 1. Right? Okay. Now we will focus our attention on finding out y. Now, if I look at the displacement in the y direction, right, I want to find out y. The velocity is not constant, so I cannot use the equation, right? This equation which I had over here was displacement is equal to velocity into time. This equation is valid only when velocity is constant, and therefore we were able to use it here. But to find out displacement along y-axis, I cannot use this equation. I'll have to use the equation s is equal to ut minus half gt square. Right? In this case, s is y is equal to, what is the initial velocity? Now, since I am finding out displacement along the y-axis, I have to take the initial velocity in the y direction. Right? The initial velocity is u, but the component in the y direction is u sine theta 0. This component is responsible for taking it in the upward direction. So here u will be u sine theta 0 into t minus half gt square. Right? Now, taking this value of t and putting it over here, I'll get y is equal to u sine theta into t is x upon u cos theta 0, of course everywhere, right, minus half g, t is again x square upon u square cos square theta 0 is equal to, now u will get cancelled out, and sine theta 0 upon cos theta 0 is tan theta, so I'll get tan theta 0 into x minus half. If I rearrange this equation, it will look u square cos square theta 0 into x square. I'll put this in bracket. Right? This is equation number 2. Okay, so we have arrived at an equation for projectile motion. The equation looks like this: y is equal to tan theta 0 x minus half g by u square cos square theta 0 into x square. If you look at this equation closely, you will find that this equation is quadratic in x, because you see here x square, and is linear in y, and therefore it is the equation of a parabola. And hence this particular path which this object has taken has a shape of a parabola. Right? Okay, this is what we wanted to achieve in this video. We wanted to get an equation for an object performing projectile motion. In the next video, we will try to find out some other parameters associated with projectile motion, like range, which is this distance OR along the x-axis, and OQ, which is the maximum distance along the y-axis, and some other parameters like time of flight. Right? We'll stop over here and see you in the next video, wherein we'll discuss all those parameters. Thank you.